Yeah, yeah, that's where we are.
All right, let's see here.
Yeah, we're actually. Actually, let me see.
I think there's a little bit of feedback though.
Oh yeah, let me. Okay, I think I got rid of it. Do you still hear it?
I think it's good.
Okay, great. Yeah. Oh yeah, you're right. Yeah, we're on page 111. Negations of universal conditional statements.
Okay. So let's see. We might have visitors in the stream today, but until they come, I guess we can just kind of go through this.
Yeah.
So let's see. Negations of universal conditional statements. I wonder, like, real quick, do you remember what the main idea of this chapter is?
This one, kind of looking generally at negating quantified statements. So earlier we looked at like for all x, p of x, how do you negate that? And then there exists an x such that p of x, how do you negate that? And so now they're looking at like kind of going more advanced, looking at universally quantified conditionals, like for all x, if p of x, then q of x. So it's kind of just looking at negations of different statements that involve quantifiers.
Oh, okay. And then did we already understand some insight about how to negate these quantifiers? Oh, like negating a universal quantifier and negating
Yeah,
a huh?
yeah, getting existential. Yeah, I guess it was like I guess the key idea was like intuitively like all of them are like this. The negation of that is there's one that isn't like this. So for all x, p of x, the negation is equivalent to there exists an x such that not p of x.
Right. Um let's see. That makes sense. And then for there exists an x such that p of x, the negation of that would be for all x, not p of x. Makes sense.
Yeah, exactly. Because the negation of saying like there's something like this is saying like everything isn't like this.
Okay. So now we're going to dive into universal conditional statements.
Yeah.
Hmm. Let's see. I guess real quick before we do that, do you have a guess as to how this is going to work? I know that with just 10% of my brain power, I don't think I could figure it out. I would have to actually think about it.
Yeah. Well, I think it might be easiest to figure it out like intuitively, like because the universal conditional statements would be like all cats are mammals, which we'd represent as like for all x, if x is a cat, then x is a mammal. So we can think like intuitively, what would the negation of all cats are mammals be? Um, and it seems like maybe like there is a cat that isn't a mammal.
Hmm.
So maybe the negation of for all x, if p of x, then q of x would be like there exists an x such that p of x and not q of x.
Oh, okay. Yeah, I think you're on something. Let's see. The negations of universal conditional statements. Negation of universal conditional statements are of special importance in mathematics. They form the form of such negations can be derived from facts that have already been established. By definition of the negation of a for all statement, not well. Let's see. How do you read this? Not,
Um,
or do you say
for
it's?
all
Go ahead. Oh, you say the not afterwards, or what are you gonna? How are you gonna say
uh,
this?
yeah, we could say not for all x if p of x then q of x, or like it is not the case that for all x if p of x then q of x.
Okay. So let's say not for all x, then p of x, or not for all x if p of x then q of x is equivalent to some x such that not if p of x then q of x. I think saying it's not the case sounds better with English grammar. I'm just curious if just using the logical would work. The
Yeah.
logical
Yeah, it
language.
would work because yeah, like people would know what you mean. Like if you kind of always read that symbol as not. Yeah, so it's
True.
still fine to say just not instead of it's not the case that.
Yeah. But okay, so there's some x
Yeah,
such that it's not the case that p of x then q of x.
yeah. So here that we're applying what was done in the previous part. Like this is a universal statement, so you can negate a universal statement by saying like you negate for all x something by saying there exists an x such that not whatever that is.
Hmm.
Like all of them are like this. The negation of that is there's something that isn't like this.
Right. I guess that makes sense intuitively. I wonder what the like series of math or like algebraic rules you would apply to get from one to the other.
Yeah. Yeah, I guess you'd have to like prove like I guess you'd have to prove it um like for any arbitrary domain, you would have to show that one statement is true if and only if the for all x p of x is true if and only if there exists an x such that not p of x is true. Or sorry, you have to show that for any possible model, like any possible domain, etc.
Well,
For all x p of x. Oh, good.
with like simple conditionals, I'm pretty sure there's a logical equivalence that's kind of similar to this. I mean, we wouldn't use the for all and the existential quantifiers, or is it, yeah, yeah. But I'm pretty sure there's a conditional that kind of has a similar transformation. Like, let's see. Uh,
Well,
well,
I guess we're
go
gonna
ahead.
use like the rule for conditionals in the next step.
Okay, so
But
it's
like to incorporate the for all and that there exists, we'd have to kind of imagine like some generic model and show that
right.
yeah, one of the thing on the left is true if and only if the thing on the right is true, regardless of the model.
Hmm.
Yeah, so you'd have to say like suppose the thing on the left you have some model like some domain for the x, some meanings for the predicate symbols, etc. Um, suppose the thing on the left is true, then show that the thing on the right has to be true too. Um, and I guess you can kind of I think earlier they had like kind of formal definitions of for all and there exists, and I guess they would use those like uh like it you have not for all x if p of x then q of x. That means it's not the case that for every x in the domain, if p of x then q of x. And I guess you would kind of just reason that like if it's not the case for every x,
Right.
that's the case,
Right.
then yeah, then there must be an x for which that isn't the case. And that's exactly what we have on the right.
I really do want to do a truth table. So, like, how long can you stay today, by the way?
I can stay for like a couple hours.
Okay.
Yeah, I don't have anything like definite. I don't have anything that I have to go to. So
So let's see. Yeah, I guess if we make good progress, maybe if we remember, we'll try a truth table using there are the two types of logic. Is this first order logic and then the other one's predicate logic?
oh, this one's first order logic, and predicate logic is another term for first order logic.
Oh, okay.
The one we did earlier with like truth tables, and or not, etc. That one was propositional logic.
Propositional logic.
Yeah,
It almost seems like first order logic incorporates propositional logic. Is that how it
yeah,
works?
yeah, it does. Yeah, like propositional logic, we have fewer ingredients, but we have those ingredients still there in predicate logic because we still have like the not, the if then, the or, the if and only if. Yeah.
Hmm. Let's see. Predicate. And then what is predicate like? How does that the meaning of that word? reflect what we're doing here with the quantifiers?
I guess like for quantifier, well, I guess quantifiers often appear with predicates. Like for all x, something is true about x, and then we can call that p of x, which would be a predicate.
See.
Um, yeah, so they're kind of generally connected to predicates.
And then with the like addition of the quantifiers, is that when you call it first order logic? Or because predicate logic doesn't necessarily use the first order symbols, does it? Or is that also encompassed by the term predicate logic?
Yeah, yeah, it is. I guess it's a synonym for first order logic. So I guess they call it predicate logic just because predicates are kind of like a major aspect of it. But uh, but yeah, it also includes universal and existential quantifiers.
Hmm. So let's see. But the negation of an if then statement is logically equivalent to an and statement. More precisely, it's not the case that p of x then q of x is equivalent to p of x and not q of x.
Yeah. So here there's kind of an implicit step that they're skipping, because like I guess they're using the fact that if p of x then q of x is equivalent to uh, q of x or not p of x, or not p of x or q of x. Um, and then they're using De Morgan's laws to kind of distribute the negation. So like the negation of not p of x or q of x is p of x and not q of x.
What law did you use to get from the negation of the conditional to the not p of x or q of x?
So that was De Morgan's law. And then we had like another rule like from propositional logic about like a conditional is equivalent like if p then q is equivalent to not p or q, which kind of reflects the fact that for a conditional to be true, either the consequent is true, or the antecedent is false. So we have not p or q.
That was the actual law, wasn't it? I can't remember which one.
Yeah, yeah, it was. I guess maybe just like I don't know if they gave it a name, but there was a law like if p then q is equivalent to not p or q.
Huh.
Yeah. So then we have like so not if p of x then q of x. You can replace if p of x then q of x with not p of x or q of x. Um, so we have not p of x or q of x.
Right.
So by De Morgan's law, yeah, by De Morgan's law, we can apply the not to both parts and change the disjunction to a conjunction. So not p of x is just equivalent to p of x, and then we have and not q of x.
Wow. So you did that really fast. Did you like look at this beforehand?
No, I guess yeah, I guess I just like seen that rule a lot.
Yeah. Okay, let's see. So, hmm. I had a comment, but we see it so often. I'm not even sure if I should like keep mentioning it. But again, um, so it's not the case that if p of x then q of x can eventually be seen to be equivalent to p of x and not q of x.
Yeah,
Um, hmm. It's tough trying to articulate this, but it's something to do with the vacuous trueness of these if statements. Um,
yeah. Well, like intuitively, you can see like the negation of a conditional is equivalent to that because like so the negation of the conditional is true if the conditional is false. There's only one case where the conditional is false, when the antecedent is true and the consequent is false. So that's kind of reflected by p of x and not q of x. because p of x and not q of
Ah,
x is going to be true when p of x is true and q of x is false.
interesting. So let's see. Substituting 3.2.2 into 3.2.1 gives. It's not the case that for all x, if p of x then q of x is logically equivalent to there is some x such that p of x and not q of x.
Yeah. So what they did there is like the 3.2.1 on the right hand side, we had not p of x, not if p of x then q of x. So they just replaced it with what what that was shown to be equivalent to.
Hmm.
Yeah, and then it kind of makes intuitive sense because like it's not the case that everything with property p has property q. Then there must be something that has property p but doesn't have property q.
Correct. That's neat. Like if I replace the whole conditional with just q, well, I guess the basic rule for applying a negation to universal quantifier is you just turn it into a existential quantifier and then apply the negation to the predicate or like to,
Yeah, like the scope of the existential, like
yeah, the
or the
scope exactly.
yeah.
If the conditional is a scope, then you're like applying to calculate it, you would just think about the rule for applying a negation to a conditional, which is I guess turning it into an and statement in which the hypothesis is true but the antecedent is false. Is
Yeah,
that is
or the
antecedent
consequence.
the consequent? The antecedent is that the same as hypothesis?
Uh, yeah, I guess it is. Yeah,
So the hypothesis and the consequent. Okay.
yeah. The hypothesis is true and the consequent is negated. Or yeah, or we're negating the consequence q of x.
Hmm. So written less symbolically, this becomes negation of a universal conditional statement. It's not the case that for all x, if p of x then q of x is equivalent to some x such that p of x and not q of x.
Yeah,
Okay. See here. Write a formal negation for statement A and an informal negation for statement B. So statement A, for all people P, if P is blonde, then P has blue eyes. So negation would be, it's not the case that for all people P, if P is blonde, then P has blue eyes, which you could also say is equivalent to there is some person such that they are blonde and they don't have blue eyes.
yeah, yeah. That'll be it.
I'm not sure if that was a, but was that an informal or a formal negation?
I guess it's kind of informal. I guess you can make it formal like the way they do it here by just saying like there exists a person p, like use the variable p for them. Like there exists a person p such that p uh, is blonde and p does not have blue eyes.
Mm-hmm. There exists a person P, or I guess you would say, let's see. I'm just curious. Would you say there there exists a people P such that P is blonde and P doesn't have blue eyes and P does not have blue eyes? And it's not the case that P has blue eyes?
Yeah, but I guess you could say person because like you're only saying that there exists one.
Huh. Right. In regular language, if you were to say, um, let's see here. Let's say someone, let's say someone hops in a pool. I guess, would it be inaccurate to say that, I guess saying some people hopped in the pool would be inaccurate? Or because people is certainly more than one person, so I'm like saying like some group hopped in the pool. I guess maybe that's what it is.
Yeah. Yeah, well, it's kind of like I think that yeah, if you know that it's exactly one person, you would say person rather than people, but I think like if you don't know whether it's one or more than one, you could use the plural by default. Like if someone is like a substitute teacher or something and they want to like they could say like I have this or like are all the students or like they might say they're going to take the attendance and see if all the students in the class are there or something like that, but maybe it's possible there's only one student in the class, but like they kind of say by default refer to the group as students because they don't know how many there are. So I think like yeah, like if you know how many there are, then you would use the plural. Unless there's exactly one, then you use the singular. But if you don't know how many there are, they can use the plural by default.
Hmm.
And I guess also if like there's zero of them, you can also use the plural. Like there are no people here.
There are no people here. Yeah. Right.
Yeah, so it's interesting that you get the plural with zero as well.
Okay. I just thought I remembered last time finding like a inconsistency in how we use the word some, but maybe I'm wrong. Cause let's see here. If you said someone said this book is good, um, you specifically put the word one after some to indicate that you're kind of saying like there exists at least one person who said this, and you're making that clear. Whereas if you said some people say this book is good, you're definitely saying the plural, like at least one people, which would mean more than one person.
Yeah,
Hmm.
yeah,
Huh, okay. Well, there's no mystery there. Maybe the mystery will come back to me if it exists. Let's
yeah.
see. Um, Solutions. There exists a person P such that P is blonde and P does not have blue eyes.
Yeah. And then we got B still.
Uh, so if a computer program has more than 100,000 lines, then it contains a bug. Well, so all computer programs with over 100,000 lines do not contain a bug. Wait a
Uh,
second. Oh, that's not exactly right. Let's see. If a computer program has more than 100,000 lines, then it contains a bug.
yeah, I think about like what kind of statement is that? Like what kind of quantifier would it involve?
What kind of quantifier? And then also, right, and it's a conditional statement. So,
So here it's kind of like really means any.
true. So, there exists a computer program um with more than 100,000 lines and that does not contain a bug.
Yeah. Yeah, exactly. Yeah, because it's a universal conditional. So yeah, that would be the negation.
Right. They used it's implicit universal.
Yeah. Yeah, so here we have, so I guess here there's kind of an ambiguity in like the English language. Like if someone, like what if someone just said a computer program has more than 100,000 lines? And it could mean like there's a specific computer program that has more than 100,000 lines. That could mean like generically any computer program has more than 100,000 lines. So could be kind of representing an existential quantifier or a universal quantifier in different contexts.
Hmm.
Yeah, yeah, so that's cool.
Didn't you say that there was some kind of like study on that? On like the command of language, like if you use something in a certain uh, with certain variables in play, you could only mean some set of things.
Yeah, I don't remember exactly, but yeah, I'm sure there must be studies about that, like kind of yeah, like studying kind of what people mean with using words in different contexts.
Yeah.
Um, yeah, yeah, because the context often helps you kind of disambiguate.
Right.
Yeah, either like the context, like the literal statement, the words around the word that you're looking at, or it could just be the conversational context, like um, yeah,
Hmm. Yeah. I think at some point maybe I like judged using ambiguous language, but now I think it's kind of cool. Like I think in Japan, like often they will actually drop the pronoun if it's obvious. So it's encouraged to just kind of like take command of the meaning as opposed to the words. Like even if the words would be ambiguous to an android, you can still like demand that the person understands what you mean by having good awareness of the context.
yeah, 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 definitely.
Interesting. But now let's see. So the relation among for all there exists and an or. The negation of a for all statement is a there exists statement. And the negation of a there exists statement is a for all statement. These facts are analogous to De Morgan's laws, which state that the negation of an and statement is an or statement. The negation of an or statement is an and statement. This similarity is not accidental. Oh, I was looking for this. Let's see. In a sense, universal statements are generalizations of and statements, and existential statements are generalizations of or statements. Interesting. I almost get it. I get how an and statement is related to a universal statement. With the existential, I kind of see the similarity. Let's see. If Q of X is a predicate in the domain D of X, is the set uh what's this X of one, X of two down to X of n, then the statements for all X in D, Q of X, and oh okay, Q of X1 and Q of X2 all the way down to Q of X10 are logically equivalent. Yeah, that's easy to see. For example, let Q of X be X times X equals X, and suppose D equals 0 and 1. Then for all X and D, Q of X can be rewritten as for all binary digits X, X times X equals X. This is equivalent to 0 times 0 equals 0 and 1 times 1 equals 1. I love this because I totally agree with that.
Yeah,
Which can be rewritten in symbols as Q of 0 and Q of 1. Right. Similarly, if Q of X is a predicate and D equals X1, X2 up to X of n, then the statements for some x and d such that q of x and q of x1 or okay q of x2 or down to q of xn are logically equivalent. Here's what I don't get. With an or statement, isn't it true that they could all be oh wait, no. If they're all false, the or statement is false.
Yeah, yeah. So
Okay.
like at least one of them has to be true for the or statement to be true. And that's kind of what we want for an existential. Like we want it to be the case that there is at least one thing in the domain that makes it true.
I see. This is equivalent to for some there exists a binary digit x such that x plus x equals x. Um, this is equivalent to 0 plus 0 equals 0 or 1 plus 1 equals 1, which can be rewritten in symbols as q of 0 or q of 1. So, okay.
Yeah. Oh yeah, so that's what you were wondering about earlier, like the connection to propositional logic.
Right. So, really, it is. Let me see here. Actually, the quantifiers are generalizations of propositional logic. So you would actually think that the quantifiers are a part of propositional logic. Predicate logic adds predicates, but in propositional logic, really the quantifiers are just like syntactic sugar.
Yeah. Yeah, exactly. Because like I guess if you had like an infinite domain, then it's easier. Like it's more compact to write for all x p of
Mm.
x. And I guess you can't like you can't list all the things in the domain and say like p of x1, p of x and p of x2, etc. Um, yeah, so it's kind of like yeah, it's a kind of compact way. Like no matter how many things are in the domain, you can say like the predicate applies to all of to this one and this one and this one by just saying for all x p of x.
I wonder if you can use quantifiers without. You can. You can use quantifiers without using predicates. Like if you said for all x. Uh, well, let's see. Does that make sense? If you say for all x q, because in ordinary predicate logic you would just say q usually, or like q and r or q and not q or something like that. um
Yeah,
so for
I mean,
all x q that would imply like a domain of x's, right? And that's not what we usually do when we first learn predicate logic.
yeah. Well, I guess we have it in we have a domain of x's in predicate logic, but not in propositional logic. But yeah, if we had for all x, p and q, I
Right.
guess that would be like yeah. I guess like in predicate logic, I guess you don't have like regular propositional symbols like that. But I guess if you said that, what it would mean is that like regardless of the value of x, p and q is true. Which I guess
Right, like on a truth table, I guess for all x's at the very least, q would be true, which I guess means q is true all the time.
yeah. Yeah, because like we don't have any x like going with the q, so yeah, like if q were like a tautology, I guess, then that would be true for all x q.
There's no, even if we add more variables here, x would exist in every case, right? Like at least when using a regular truth table, like if I add y, it would double the amount of x's. Like, um, let's see here.
Yeah. Although I guess the x like the x wouldn't necessarily take truth values as its values. It could take like anything as its values.
Really?
Yeah, because like x could be like equal to like different cats or something, or it could be equal to like natural numbers, like because x can have all sorts of domains, like the domain is kind of specified. So like the domain could be like the set of truth values, but it could also be many other things. So like for all x, you would be just looking at like whatever the possible values of x are. They could be numbers, they could be like all
Right.
different kinds of objects, they could be anything.
So let's see. But just like a spoiler, I'm guessing first of all, like this just never happens, right? You never say for all x q in our whole mathematic journey. You'll never encounter this in the literature.
Yeah, I think yeah, it's not really done yeah, because in predicate logic, you don't have propositional symbols.
Right.
Yeah, because like of using propositional symbols, people will kind of like provide more structure by saying like q of x or something rather than just saying like some proposition.
Right. And in this case, I didn't even mean a proposition. I just meant a statement is true.
Yeah, and I guess like, maybe occasionally people do it like but it's not usually that useful to like include um propositional symbols because sometimes propositional symbols are considered to be zero place predicates like uh like q of x is a one place predicate because it applies to one thing.
Right. Right.
q of x, yeah, like q of x and y is a two place predicate because it applies to two things. And then some people will say like in their predicate logic that propositional symbols are zero place predicates. They're predicates that don't apply to anything, like just to kind of consider them to be predicates too. So I guess like if
Hmm.
you're doing that, you could say for all x q, but it maybe wouldn't be that useful because then like it would have to be the case that for that to be true, then q would just have to always be true. But as it's stated, if q is just a propositional symbol, then like it could be true or false. I guess for all x, q would be true if the domain of x is the empty set, because then it would be vacuously true. Like for any x value, q comes out true because there are no x values.
Right. If if let's see, if x is the empty set. Huh.
Yeah, and that's what they talk about in the next section.
Interesting. Okay, let's see. Vacuous truth of universal statements. Suppose a bowl sits on a table, and next to the bowl is a pile of 5 blue and 5 gray balls, any of which may be placed in the bowl. If 3 blue balls and 1 gray ball are placed in the bowl, as shown in figure 3.2.1, A, the statement all the balls are in the bowl are blue would be false since one of the balls in the bowl is gray. Now suppose that no balls are all at all are placed in the bowl, as shown in figure 3.2.1b. Consider the statement all the balls in the bowl are blue. Is this statement true or false? Um, let's see. The statement is false if and only if its negation is true. Okay. The negation is there's at least one ball in the bowl that's not blue, right? There exists a ball in the bowl that is not blue. This
Yeah,
is pretty trippy again because the intuition here saying all balls in the bowl are blue, you'd think that that would be
yeah, that like in
false.
ordinary English. Yeah, in ordinary English, if you talk about like all the balls in the bowl, then you're implicitly assuming that there are balls in the bowl.
And maybe that's the reason why you would think it's false. Strictly because we're assuming that there's something in the bowl whenever you say this.
Yeah. Yeah, and like in linguistics, people sometimes call that background assumption or presupposition. Um, and then some people say like if the presupposition is false, then the statement doesn't have a truth value. Like if there aren't any balls in the bowl, then all the balls in the bowl are blue. It just doesn't even make sense. So it doesn't have a truth value.
And you said because what?
Because oh yeah, so like you said, all the balls in the bowl are blue. Usually, when someone says that, they're assuming that there are balls in the bowl. Um, so that background assumption that there are balls in the bowl is a presupposition. And then some people argue that, like in ordinary English, if the presupposition is false, then the statement doesn't have a truth value. So like if there are, if it's not the case that there are balls in the bowl, then all the balls in the bowl are blue is kind of an incoherent or nonsensical statement, and it doesn't have it. It's not neither true nor false. But
Interesting.
in math, it's true though.
So, in what field is it neither true nor false?
That would be like in linguistics, like in semantics, like
Oh,
theories of natural language. Some people say that.
interesting.
Yeah, but in math language, it's true.
It's true. It's true. And at least one reason why it's true is because its negation is false, right?
Yeah.
And its negation is false. Let's see. The reason its negation is false is because it has a truth table with a finite number of truth values such that it can be negated um wait
Yeah.
if I'm saying this correctly here, because I think multiple truth values, can that be negated? it, it can be, right? Isn't it just the exact opposite for
Yeah.
all truth
Well,
values? Yeah.
yeah. Well, in this case, like what we had earlier with like representing a universal statement as a conjunction and an existential one as a disjunction. I guess we technically can't do that here because um, we were able to do that before because we had like some things in the domain. So if we had like x1, x2, or like a, b, and c in the domain, then we could say for all x, p of x is equivalent to p of a and p of b and p of c. But here there's nothing in the domain, so we can't express these as conjunctions or disjunctions.
Let me see what you're seeing here. So there's nothing in the domain, so we can't use a conjunction or a disjunction. There's no variables.
Yeah. Yeah, but we can still kind of like understand what they mean. Like um yeah, but yeah, it's like using the rule for negation. The negation of all the balls in the bowl are blue is there exists a ball in the bowl that is not blue. And for there exists a ball in the bowl that is not blue to be true, there has to exist a ball in the bowl, but there's no balls in the bowl, so that's false.
Right, right.
Yeah,
Okay,
so
which makes this
yeah, so the
true.
negation, yeah, exactly.
So how do we get the negation of this, like, without just relying on our intuitive understanding? Is there not, how would you express this first of all with symbols? Um I mean, I guess maybe it's not a requirement that it has to be expressible using conjunctions and disjunctions.
Yeah,
Obvious.
well, wait,
Go ahead.
yeah, well, I guess you could say like for all balls in the bowl X, X is blue. Because that would make the domain empty because the domain is the set of balls in the bowl. I guess you could have also expressed it for all balls X. If X is in the bowl, then X is blue, but then we wouldn't have an empty domain because there are balls out there. Um, but yeah, for all balls in the bowl X, X is blue, then we have an empty domain.
So to use conjunctions with an empty domain, I wonder what does this syntax look like? Well, first of all, what did it look like whenever the domain wasn't empty?
Well,
Um,
I guess when the domain when it wasn't empty, like if you had the domain is the set of A, B, and C, Then for all x, p of x, that's equivalent to p of a and p of c, and p of b and p of c. So you kind
Okay.
of like take a conjunction of the predicate applied to the predicate symbol applied to the different things in the domain.
And then, right, that huge conjunction was the statement.
Yeah,
So in this case, it can't be expressed this way, right?
yeah, because there's nothing in the domain.
Interesting. Okay. So interesting. I was gonna say, I guess we're lacking. Are we lacking a way to express this using, well, but then again, maybe having the quantifier is good enough for our way to express the empty.
Yeah, yeah, I think the quantifier is enough. That's probably why the quantifiers aren't just defined um, in terms of propositional logic, because
Right.
it's not always going to work, and it's also not going to work um, if you have like an uncountably infinite set for your domain, because um,
Right.
yeah,
Well,
like
can you just use a variable like n or some variable to represent infinity at the end of your like here in your, what is this? Is this the set builder notation?
it's like I guess list notation, like kind of listing them all out.
And then
Um,
also here,
yeah,
using the ellipsis.
yeah, yeah. But the thing is, like, if you had like an uncountably infinite set, like the real numbers, I guess you might run into problems representing a conjunction of all the like has like as many conjuncts as there are real numbers, because you can't really list the real numbers like in a way that's going to include all of them.
Not even with ellipses?
Uh, I
Not
guess
not
because like
easily, huh?
yeah,
Because
yeah, I
they're
think
not countable. So how would you get the next real number? Is that what you mean?
yeah, yeah, because like there is no next real number.
Ah,
Yeah, because like you have 2.5, then you have 2.75, but you've got stuff between them, and then if you pick something between them, you still got some further things between those.
but the universal quantifier catches all of that.
Yeah,
That's really fascinating. Because yeah, it's really fascinating. It's like a statement. It's like saying, yeah, like saying all, and you don't have to do the little counting thing first that you would when you're doing the conjunction.
yeah,
Hmm.
yeah.
I wonder if the existential quantifier also provides some kind of extra expressiveness that you can't do with the disjunctions.
Yeah, yeah, I think it does because like in the same scenarios, you wouldn't be able to use disjunctions like with an empty domain or an uncountably infinite domain.
Hmm. But then how? So for example, oh, an uncountably infinite domain. Yeah, I guess so.
Yeah,
Yeah.
yeah, 'cause you're not able to like list them in that way. And then also if you had an empty domain, like you wouldn't be able to do the disjunction because you don't have anything in there to apply the predicate to.
What's an example of a statement involving an empty domain and an existential quantifier?
Um, there is a unicorn in this room. There exists a unicorn X such that X is in this room.
Okay, so the domain of unicorns is empty, but you're able to express the statement there exists a unicorn X,
Yeah.
um, such that P of X being the unicorns in the room.
Yeah.
So it's, let's see, it's a false statement, but you can't say the same statement with the, let's see, with the conjunctions. You can't, huh? So you can make false statements with conjunctions. Like if the domain was not X and not Y, and your conjunction your disjunction was X or Y, I suppose it would be a false disjunction. Um, but when the domain is empty, you can't even create a false disjunction. You can't even express a false disjunction, right?
Yeah, yeah, because there's nothing like to put in the disjuncts.
Right, but you could still use the existential quantifier
Yeah,
to at least make a false statement.
yeah,
Fair enough. So let's see. If the statement is true or false, is the statement true or false? The statement is false if and only if the negation is true. The negation is there exists a ball in the bowl that is not blue. So negation is false, therefore it's true. And I guess that's just a rule all throughout mathematics, right? If the negation's false, then the statement's true.
yeah, yeah. We already had that in propositional logic. Yeah, so that's kind of propositional logic being incorporated into predicate logic there.
Hmm.
Yeah,
Okay.
that comes from the truth table of negation.
Comes from the truth table of negation. I like that. It almost feels like that implies something about the framework of logic that I'm only seeing a small window of right now. But like, if the negation's false, then the statement is true.
Yeah, yeah. It's kind of like that's just how we defined not. Like the truth table is pretty much giving the definition of negation. And the definition is pretty much like um, not P is true if and only if P is false.
Right.
Not P is false if and only if P is true. And that's kind of something that's just stipulated. It's kind of just assumed, but as the definition of negation.
Interesting.
Yeah, so it's not something that's proven. It's just kind of assumed as a definition.
Huh. Hmm. Okay. I guess like the only kind of caveat with that is if you're trying to create some results in the real world, you gotta take into account that a vacuously true thing is true in such a way that it like it wouldn't be able to produce results or like have an impact on like the physical world the way ordinarily true things do. Like huh, it's sort of a more
Yeah.
irrelevant kind of truth. Like if you say there exists a blue unicorn and there actually does exist a blue unicorn, that has implications. If you have some kind of plan in motion that involves the blue unicorn in some way, like maybe you need to utilize it to gain access to a new world. Well, you can do that. But if your statement is all unicorns are blue, or hmm,
Yeah, no, it kind of like just be true vacuously, but it wouldn't really say anything interesting. I guess in modern like linguistics, people do say like when you say all unicorns are blue, you're kind of like talking about all unicorns in some world that's different from the actual world. A world where unicorns do exist. Um,
hmm.
But there's also the idea of vacuously true universal statements reminds me of like Hearthstone. Like when you play a card in Hearthstone, it's supposed it's always gonna work. Like it always meaning what's on the card. Um, it's always true that what the card says is gonna happen happens when you play it.
Right.
Um, so like if you play a card that says destroy all minions and there are no minions on the board, you can still play it, but it just won't do anything. But the card worked, so it's like considered to be true that you destroyed all of the minions, if there are no minions.
I guess that's neat. I actually like that a lot more because your deck is used in a lot of different universes, or it's used in a lot of different contexts. So in some universes, like your deck will have cards that have vacuously true meanings, and in others, those same truth tables will have an impact. So, you know, that actually seems like a more realistic way of looking at how vacuously true statements make their way into our lives. Interesting.
Yeah, exactly.
So let's see. But the only way this negation can be true is for there actually to be a non blue bowl in the bowl, and there's not. Hence, the negation is false. And so the statement is true by default. In general, a statement of the form for all x and d, if p of x then q of x, is called vacuously true or true by default if and only if p of x is false for every x and d. For all x and
Oh
d.
yeah, so here they're doing something kind of different. They're thinking about it in kind of a different way. So what I was saying was like if we have for all x and d p of x, then that's vacuously true if the domain of x if d is empty. But
Mhm.
here they're saying like another thing for all x and d if p of x then q of x, if p of x is false for everything in d, then the statement is vacuously true. Which is kind of like a similar idea because like we have there are two different ways of expressing all the balls in the bowl are blue. You could say for all balls in the bowl x, x is blue. In that case, it's vacuously true because the domain, the set of balls in the bowl is empty.
Right.
But you could also express that as for all balls x, if x is in the bowl, then x is blue, which is how they do it here. In this case, the domain isn't empty, but the antecedent of the conditional in the universal conditional statement is false for everything in the domain. So that means so that also makes it vacuously true. So I guess that's another idea of being vacuously true. Yeah, and that
Hmm.
kind of that makes sense because in the sense that like uh, if p of x is false for everything in the domain, then that means like when the antecedent is false, the conditional is true. So that means for everything in the domain, the conditional comes out true, which is going to make the universal statement true.
It's only vacuously true with a universal statement if the antecedent is false for all x's in the domain, right?
Yeah. Or yeah,
Otherwise,
that's going to be vacuously true. Yeah.
otherwise it would be false.
Yeah. I mean, it could be true also if p of x is true for some of the things in the domain, and then in each of those cases, q of x is also true.
You're right. So, okay, yeah.
Yeah.
So it's I get you. It's only vacuously true in this case if p of x is always false.
Yeah. Yeah, and it's kind of like if you say all humans with wings can fly, and you can say it's vacuously true because the set of humans with wings is empty. Or you can say it's vacuously true because um, for every human, it's false that they have wings. So then it's also true by default for that reason.
Hmm. Yeah, fair enough. Maybe it's a little different from the Hearthstone example. Since with the Hearthstone, it almost seems more like if there are minions on the field, they'll be destroyed. Like if the card actually says all minions on the field will be destroyed, but there are no minions on the field, you could say it's vacuously true. But it almost
Yeah,
seems like it's acting like if there are minions on the field, then they'd be destroyed. Then they'll be destroyed. What I mean is, in the cases in which there are minions on the field, the statement seems to have like some soundness. Whereas when I say like all humans with wings can fly or all humans with wings can blow up the moon, in a universe where humans do have wings, I don't see how that would be a possibility.
yeah,
Um, so I don't know. Maybe the nature of these two vacuously true statements is a little different. Just
yeah. Yeah, I mean, I guess unless you say like for all things D, like use the most generic thing, you could express the minion one as a universal conditional if you're just like for all objects D if X is a minion. For all
right,
objects X if X is a minion, then it's destroyed. But to make it look more like a universal conditional, you could say like destroy all minions with taunt. In that case, when you play the card, it's got to be true that all minions with taunt are destroyed. And maybe there are minions on the board, but if all of them are like not with taunt,
right.
the that's where them having the statement that they have taunt is false. And then it would also be vacuously true that all of the ones with taunt are destroyed.
Interesting. So, yeah, both of these types of statements are vacuously true. One just seems like it would be sound in some universes, and it just may coincidentally, we may be in a universe in which it's vacuously true. And the other one is still vacuously true, but I believe, according to like the other rules of reality, it would actually be a contradiction for it to ever be true in any universe that like all humans with wings can blow up the moon.
Yeah,
That's like it's impossible.
yeah, yeah. So that kind of reflects another difference between math language and ordinary language.
Right,
Yeah,
but at least in both of those statements, like even with the taunted creatures being destroyed and there's no taunted creatures, I guess they are both vacuously true though.
yeah. Yeah, and also when it comes to like laws, I guess implicitly it's being assumed that someone is following the law if the law doesn't apply to them.
Ah,
like if the law says like you have to file reports on all expenses of some certain kind. If you don't have any expenses of that kind, then you haven't broken the law. Um,
right.
yeah, otherwise that would be a problem if like whenever like if they were vacuous considered vacuously false or something. Then everyone will be breaking lots of laws all the time just because like the whatever's being quantified is something that they don't have.
Right. Hmm. Okay. Without thinking about it, I wonder if like innocent until proven guilty is a vacuously true situation.
Uh, yes,
How exactly is it different if it is? The law one certainly is vacuously true. It's like true that you're following the law because like if the law doesn't pertain to anything that you have
yeah, yeah,
like and it's a situation where if you're not breaking the law then you're following it.
yeah, yeah, exactly. Yeah, so like there has to exist like if the law says like for all things of a certain kind, you have to do this with them. and there are no things of that kind, then you're not breaking the law. For you to break the law, there has to exist a thing of that kind where you don't do what's required with it.
Right. And to follow the law by definition means to not break it.
Yeah, exactly. And that kind of reflects the idea that like you break the law if the negation of what it said, if the negation of what it says you should be doing comes out true. Like you do this, like if you're following the law says do this. If the negation of you're doing this is true, then you're breaking the law.
Right.
Yeah. So that reflects the idea we had earlier that like a statement is false if its negation is true. A statement you're following the law is false. If the negation is, in those different cases is true. But I guess with innocent until proven guilty, not sure if it will be vacuously,
Hmm.
in what sense it might be vacuously true. Um,
I sense there's a difference. I wonder if we can find what it is.
yeah, because like I guess if we say it as conditional, everyone who is not, or for all people X, if they have not been proven guilty of a crime, then they're considered to be innocent. If X has not been proven guilty of a crime, then X is considered innocent. Um, and I guess maybe if someone um, like I guess if that would work though, because that would just be like then if no one has been proved if no one has like if no one has failed to be proven guilty of a crime, then the statement is or
Hmm.
if everyone has been found guilty of a crime, then the statement everyone is innocent until proven guilty would be vacuously true.
If everyone is proven guilty of a crime, then the statement everyone is innocent until proven guilty. Oh, yeah, that would be vacuously true by definition.
Yeah.
Well, the statement um is a statement if everyone is innocent, then everyone is not proven guilty. Or the statement is basically if everyone is not proven guilty, then everyone is innocent. I think that's what it is, right?
Yeah. Or like yeah for all X, if X is not proven guilty, then X is innocent. So everyone who has not been proven guilty is innocent or is considered innocent.
Mm-hmm. So for it to be vacuously true, it has to be universal in which everyone is proven guilty. Let's see.
Yeah.
Hmm.
I guess there could also be a universe where there are no people. Then it would also be vacuously true because then there are no people who have been proven guilty or who have not been proven guilty.
I guess I meant more in terms of one person being innocent until proven guilty.
Yeah. Yeah, so this particular person, if this person X is if X is innocent, then X is or if X has not been proven guilty, then X is innocent. But I guess in that case, if you have were it just one person, then there wouldn't be a universal quantifier.
Um, I mean, I guess the universal quantifier, like the domain, could be all the seconds in that person's life, all the moments
Oh
that
yeah.
make up their case.
Oh yeah. So if they are not proven guilty of a crime at like each moment, so you're quantifying over moments. Um, yeah, I guess maybe then it's vacuously true if they have been proven to be committing a crime at every moment in their life, I guess.
The statement is vacuously true. You said wait, let's see. Innocent until innocent until proven guilty is the same as
If they're not proven guilty, then they're innocent.
which is um okay, which is vacuously true if or what did you say? Did you say the negation of this or what did you
Or, well, I guess it depends how you understand it. Like, if the statement is saying like every person who has not been proven guilty is innocent, then we have for all x, for all people x, if x has not been proven guilty of a crime, then x is innocent. Um, uh, but and then in that case, it's vacuously true if everyone has been proven guilty of a crime, or if there are just no people at all. Um, but
huh.
but you were talking about kind of like an alternative, like where it's referring to just one person and like you're quantifying over moments in their life. In
So
that case, it would be what?
it's only vacuously true if there's no people in your first example. Right.
Uh, yeah, it was vacuously true if there are no people, and it's also vacuously true if
There are no
every person.
moments. Oh, go ahead.
Oh, well, in the case where it's like referring to all people, like yeah, it's vacuously true if there are no people. It's also vacuously true if everyone has been proven guilty of a crime. Um, um,
Right, right.
yeah, and I guess when someone says innocent until proven guilty, they also have like like in minds like some fixed crime. It's like if someone's proven guilty of
Right,
one
right.
crime, they're still innocent until proven guilty if they're accused of another.
Mhm.
So I guess you would have to technically say like um,
Hmm.
for all crimes, for all people, if the person has not been proven guilty of that crime, then they're innocent of that crime. So you have to have like for all C, for all X,
Hmm.
for all crimes C, for all people X. If X has not been proven guilty of C, then X is innocent of C. Um, so I guess if they're in a world where no laws and no crimes, I guess it could also be vacuously true.
Right. Interesting. But in reality, it's not vacuously true because there are people, there are crimes. So it's true, but not vacuously true.
Yeah, yeah, exactly. And there also are people who have been proven guilty, or who have not been proven guilty of a crime. So, because that's the other way it could be vacuously true. It could be vacuously true if just everyone has been proven guilty of a crime,
Everyone
or
has been
whatever the
proven
crime.
guilty.
Yeah,
Right.
or I guess
There's
actually, if everyone actually it would be if everyone has been proven guilty of every crime. So that's
um
unlikely, but
really?
if there's yeah, like if there's because we had like for all
Oh,
C,
I
for
see.
all yeah. So I guess maybe if there's a law where there's only one crime, maybe that could happen that everyone's and there are only like two people, maybe both of them have been proven guilty of that one crime.
Right.
But yeah,
Hmm.
yeah. So if there's no crimes, no people, or everyone has been proven guilty of every crime, then it would be vacuously true.
Yeah. I suspect this is one of those situations where we probably say like for every crime, perhaps, but not for every person. Like it just be implied that the principle applies to all people. So like you could say for every crime C, P of C, where P of C means people are not guilty unless proven guilty.
Yeah, yeah. You could have defined PFC to be that more complex statement.
And
Yeah, yeah, and yeah. People do often use shorthands, like using like a simpler statement to represent something more complex that's implicitly understood.
yeah, but then I guess you'd also be able to simplify for all crimes. So let's see. But
Yeah.
I guess
Well, like if someone says innocent until proven guilty, they're implicitly assuming like for all crimes, but they
for
don't
all
say it.
people as well. Right.
Yeah.
Interesting. Okay. But there is no vacuous truth that we can find here. Like, um, a person is innocent until proven guilty. It's not. There's no vacuous truth here, and because it's more like true in all cases. It's true because it's true in all cases, not because there are no cases, and not because the hypothesis of all cases are false. It's true in all cases in which the hypothesis is true, and there are some cases in which the hypothesis is true. The hypothesis being some person has not been proven guilty for some crime and they are innocent. And they are, yeah, innocent. So, anyway, okay. Does that make sense?
Oh, was I muted actually?
Um,
Because I couldn't hear you for like a couple minutes, and I opened my screen and it was kind of looked like it was disconnected for a second.
yeah, I think it just disconnected for a second. But I do hear a little bit of feedback again.
Oh, okay. Let's see.
Well, no, yeah.
Oh, what about now?
Let's see. Testing. Seems good.
Okay, yeah. Um, yes. What part of what I said did you get,
So,
or did you hear?
what were you saying
And
last?
also, you might have said you might have said something that I missed too. I guess
Right.
I just read that last paragraph about the meaning of in general.
Oh, try reading it again then.
Oh, okay.
So,
Okay. What were you saying, by the way? Was there anything else you were saying about like the idea of vacuously true? Or...
just that we figured out that the statement like innocent until proven guilty, I we weren't able to find any vacuously true cases because in order for it to be vacuously true, um, like you said, it depends on how you look at it. If you look at it in terms of all people and all crimes, vacuously true, vacuously true would mean either there's no crimes and no people, um,
Or that every person has been proven guilty of every crime.
right. And in terms of an individual, like, do you think that innocent till proven guilty is vacuously true for anyone? For it to be vacuously true for someone, it would have to mean that they're guilt. Would it have to mean that they're guilty of they were proven guilty of the crime?
Yeah, well, it could also be like for a baby, no laws apply to them, so they can't like
Hmm.
yeah, in that case it's kind of like there are no
Hmm.
crimes that they could commit, so that could be another reason why it's vacuously true for a person.
If there are crimes, then it's not vacuously true for that person, right? Why is that?
Yeah, or if there are crimes that they can commit, and like there are some crimes that they haven't been proven guilty of, then it's not vacuously true for them. Like if there are crimes that they could commit,
And some
then it would
crimes
only
that
be
haven't been proven
vacuously,
guilty.
yeah, it'd only be vacuously true if they've been proven guilty of all of them.
Innocent until proven guilty, or not guilty. So innocent until proven guilty. For it to be vacuously true, the hypothesis has to be false, right?
Yeah, yeah. If we have it like for all x, if p of x, then q of x, yeah, p of x has to be false for everything in the domain.
And our p of x is what?
Um, x has been proven guilty of crime C.
Okay, so the statement is actually um, for all crimes and all people. If the, well, in simple terms, like if a person commits a crime, then they're guilty. Is
Yeah, or actually, sorry, I guess the p of x would be x has not been proven guilty of crime C.
okay. If X
Yeah,
has not been proven guilty of crime C, then X is innocent for crime C.
yeah, yeah, and then x has not been proven guilty of crime C. For that to be false for any x and C and C, then that means that x has to have been found guilty of every crime.
Let's see. Right. For it to be, so X has to be found guilty of every crime. For it to be vacuously true. And then let's review again why, when we're dealing with universal quantifiers, the hypothesis has to be exhaustively false before we can apply vacuously true.
Yeah, well, it's kind of, I guess in part it's kind of just a definition of what it means to
Right.
be vacuously true. But I guess we can think about why is it called vacuously true in that case. Well, I guess maybe it's called vacuously true because like if the hypothesis is false for everything in the domain, then it's almost like the statement doesn't really tell us anything. Like in a world where everyone has been proven guilty of every crime, if you say like everyone who hasn't been proven guilty is innocent, then that doesn't really tell you anything because like that's not going to really tell you anything about any individual.
Interesting.
Yeah, so maybe that's why it's called vacuously true. But yeah, I guess fundamentally it's just a definition.
Mhm. Okay, okay. It's enough exercise on that example. Now let's see. Well, that was really nice.
Yeah. Yeah, and then I can read this last paragraph about in general. So, by the way, in ordinary language, the words in general mean that something is usually but not always the case. In general, I take the bus home, but today I walked. In mathematics, the words in general are used quite differently. When they occur just after discussion of a particular example, as in the preceding paragraph, they are a signal that what is to follow is a generalization of some aspect of the example that always holds true. So the idea is like in ordinary language, if you say something is true in general, it could just mean it's like it's usually true. Um, but if you in math, if someone says like they give like a specific example and then they say like in general this is the case, what they mean is that like something about something that was illustrated in the particular case of the example is also true universally. So they're kind of
Oh,
generalizing in that way.
it's like it's saying it's also true generally.
Yeah, yeah, exactly. Yeah, where generally means like always, not just usually.
Interesting. Okay, so now what exactly does general mean? Like if we if we just are you expanding the domain to something else? You're
Oh.
expanding it to a bigger domain, right?
Yeah, I guess we can see like kind of in the example what's going on with in general. Like so we got let's see what page. Um, yeah, so we got like yeah, so they looked at like a specific statement. Um, all the balls in the bowl are true. Is vacuously true. If there are no balls in the bowl. Um, and then they're
Hmm.
like, in general, a statement of the form for all x and d if p of x and then q of x is vacuously true in this situation. Um, so like they give a specific example of a universal statement that's vacuously true, and then they're like, in general, any statement that has uh, like this form ends for which um, the antecedent is false for everything in the domain is vacuously true. So they're kind of like they gave a specific example of a statement of a certain kind, and then they're like, for all statements of that kind,
Right.
it's vacuously true in this situation.
Yes. So whenever you use the word generally, you could also mean like for all other things of this kind, the rule applies to them as well, right?
Yeah.
Hmm. Okay. I can't think of an example in which you take something like a specific example, a rule that you're applying to a specific example, and you bring it back to its principal structure that a bunch of other examples um, are a part of, and yet it's only true for the specific one and not for the other ones. Like it's not true generally. Uh,
Yeah. Well, um,
in order for that to be the case, like it would have to be something that's like contextually bound to that one example, right?
yeah, because like you could say like all cats are mammals is true, but it's not the case that in general any statement of the form for all x p of x is true.
Right. Right.
Yeah.
Okay, okay, I like that.
Yeah.
Now let's see. Variants of universal conditional statements. Recall in section 2.2 that a conditional statement has a contrapositive, a converse, and an inverse. The definitions of these terms can be extended to universal conditional statements. Consider a statement of the form for all x and d if p of x then q of x. Its contrapositive is the statement for all x and d if not q of x then not p of x. Its converse is for all x and d if q of x then p of x. Okay. Its inverse is for all x and d if not p of x then not q of x.
Yeah. This is kind of the usual definitions of contrapositive, converse, and inverse, just applied to universal conditionals.
Okay. Hmm. I wonder what small differences we'll see here. I know, like with the vacuously true, the difference is when you're dealing with universal statements, it has to be the hypothesis would have to be false for all for all elements in the scope of the universal, right?
Yeah.
Or the domain would be empty. And both of those
Yeah.
nuances didn't really apply back in the pure propositional logic, propositional
Yeah.
conditional logic.
Yeah.
Hmm.
Yeah. I
Okay.
guess in propositional logic, they might have said like we have if p then q, that's vacuously true if p is false.
Mhm.
Yeah, so in that context, we had the idea of vacuous truth with propositional logic as well.
Right. And I guess in propositional logic, if P, like the P represents like, is equivalent to the universal statement in which every P um, has some truth value. So with the propositional logic, if P then Q, that would help us express, I guess, for all X, well, let's see here. In propositional logic, P might be equivalent to, in the two situations in the universal logic, one in which all P's are false and the other in which all P's are true. It couldn't, in propositional logic, you couldn't, I don't think you would attempt to represent like a situation in which like half of the P's are like it P of X is true for half of the X's in the domain and not true for the other half. It's impossible.
Yeah, 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 exactly.
Um, yeah, like you can't get vacuous truth in universal statements unless all of the P of X's are false. The
Yeah,
There's like the little grouping mechanism at work. Even if they were mostly false, um, unless I'm thinking about it wrong. So like maybe the universal statement is actually a group of propositional statements. And so there's several vacuously true statements. Or there could be. Like let's say you have a domain that has three things in it. And you have a universal statement for all x if p of x then q of x. And let's say p of x is false in two of the three cases. On one hand, by definition, here it sounds like the universal statement clearly is not vacuously true. From another perspective, you could say that there are two vacuously true uh, cases.
yeah,
Two out of three of the
yeah,
cases are vacuously true.
yeah, yeah. That would be the case. And then like if p of p of every for each thing in the domain p of x, or for each x in the domain p of x is false, then you can represent the conditional as, you can represent the universal conditional as um uh like if the things are a, b, and c, if p of a then, or if p of a then q of a, if p, and if p of b then q of b, and if p of c then q of c, and each of the conditionals would be vacuously true in the propositional sense, where the antecedent is false.
Right.
So then, yeah, with all of the conditionals being vacuously true, the whole thing is vacuously true.
Hmm. So, what would you call those individually vacuously true statements? Obviously, you wouldn't say the universal is vacuously true. Would you say the propositional? Like, how would you refer to an individual?
Oh, they be called instantiations.
Oh,
Like, yeah, so like if you have for all x p of x, then if you plug in a particular value in the domain and say p of a, then p of a would be an instantiation of the universal.
interesting. Is that like an official term? It definitely works.
Yeah, yeah, I've seen that term.
Interesting.
Yeah, or maybe instances is another term that's sometimes used. Instances or
Yeah.
instantiation.
Oh.
Yeah, so a universal statement is true exactly when all of its instances are true.
Right. I like that concept a lot. It helps me understand when a universal is true. Without the understanding of instances, I'd be forced to just take the truth, the definition of the truth of a universal statement, um, um, at face value or whatever.
Yeah,
But that makes a lot of sense. So,
yeah,
in terms of its contrapositive, a universal statement can have a contrapositive. I know
yeah.
that
Although
in
I guess,
instance definitely can, right?
yeah, and I guess like I think maybe most people wouldn't necessarily call that the contrapositive, because like some people would say like only a conditional can have a contrapositive. Technically, for all x and d, if p of x then q of x isn't a conditional, it's a like a universal, like a universally quantified statement with a conditional in its scope. But I guess maybe just like for convenience, and shorthands, they use the same terms for conditionals as for universal conditionals as they do for conditionals. So like the contrapositive of a universal conditional, they're just calling it the universal conditional where you replace the conditional part with the contrapositive.
So what were you saying? Like a universal statement doesn't have a contrapositive? All right.
It's just like a sorting. Well, it's a matter of terminology. Some people would say would not. Some people would say only a conditional has a contrapositive, but I guess it's just a matter of how the word is used. I guess. I guess you can't like just for shorthand. They're just defining the contrapositive of a universal conditional statement that way. And I guess in math you can define things however you like. So, um, but I guess just that definition isn't always used.
Huh. I wonder if the contrapositive has some value here. I wonder what the value is. So
Yeah, I think that comes out on maybe on the next page they talk about that.
interesting.
Yeah, but now they give us some practice just writing the different contrapositive, the converse, and the inverse.
Okay. I know the contrapositive is always logically equivalent to the original statement.
Yeah,
So let's see. Write a formal and informal contrapositive, converse, and inverse of the following statement. If a real number, we could say, if any real number is greater than 2, then its square is greater than 4. So for any real number, if its square is not greater than 4, then it is not greater than 2. Then the number is not greater than 2. Or
yeah,
for any real number x, if the square of x is not greater than 4, or you could say if x squared is not greater than 4, then x is not greater than 2.
yeah,
Um, okay, the converse. So for any real number x, if x is greater than 4, or if the square of x is greater than 4, then x is greater than 2. In the inverse, for any real number x, if x squared is not greater than 4, oh wait, no. If x is not greater than 2, then x squared is not greater than 4.
yeah,
Hmm. Okay. I think that, I guess now to write the informal ones. I think this does come in handy in ordinary language because people throw around universal statements a lot, and it's normal in spite of how inaccurate a universal statement you think would be on average. I think it's used quite often. So I
yeah,
suppose yeah, like a mastery of the contrapositive, converse, and inverse of universal statements is proportionally useful to how often it's universal statements are used.
Yeah. Yeah, I think they're used all the time. Like everyone uses them.
Right, I can't help but use it.
Yeah. Yeah, without itself would be a universal statement that isn't necessarily true.
Right. Hilarious.
Yeah.
All right, so
Yeah.
the formal or the informal. So the original statement, if a real number is greater than 2, then the square is greater than 4. Contrapositive, if a real number is, if the square of a real, like, would I say, I think, would it be cheating to say if the square of a real number is not greater than 4, then the real number itself is not greater than 2?
Yeah, I think that's good. Yeah, that's an informal way of expressing the contrapositive.
Okay. So in their example of the contrapositive, they did not actually change the universal variable. It says for x in basically all of their examples. In the original one, it says for x and d, and the contrapositive also says for x and d. Whereas what I did
Yeah.
was I changed it from saying for x and d to like for y in um d prime basically.
Oh yeah. Well, I guess like it doesn't really matter what letter you use for the variable, because that doesn't affect whether statement is true or not. So you can use y or x. If you still used x, it wouldn't make a difference. But I guess if you're doing the contrapositive of like for all x and d, contrapositive would involve the same domain, so it'd be d rather than a potentially different d prime. Because we're assuming that
Oh,
like for a universal conditional statement, the domain we're kind of keeping the domain constant. So the contrapositive would be like you take the contrapositive of the scope, the conditional and the scope, but you keep the domain the same, still quantifying like within the same domain.
interesting. I guess what I meant is like x, I was referring like x and y, x being the number itself, y being its square. So
Oh yeah.
I'm almost saying I'm saying for all squares as opposed to for all x's, which
Well,
seems to be of a slightly different form than what they have up there.
yeah. Well, I think you said like if the square of a real number is not greater than four. So yeah, I guess the square is the subject, but like of a real number, we're still kind of quantifying over the real number.
Huh.
Like of any real number is the idea, because like even there they have its square. The square is the subject of the sentence of the second part of the conditional. But you're still quantifying over real numbers if you say like if the square of a real number.
So you mean like the domain is still good, right?
Yeah, yeah, because you're still talking about like if the square of any real number is like this.
Yeah.
So yeah, the kind of in that case it tells you what you're quantifying over.
Interesting. And you think that, I guess, keeping the domain the same is all that really matters in
Yeah,
terms of being consistent with the rules up there? I mean, obviously the meaning is the same, but I really never looked at it that way. So, okay.
yeah. Yeah, and then like if you in the formal language you would have like for all x in R, if x squared is not greater than four. So in that case you would still have the x showing up.
For all x and r, if x squared is not greater than 4. Right.
Yeah,
Then
then
x
x is
is,
not greater.
yes.
Yeah, and then also you could also potentially say is less than or equal to instead of not greater than.
Right. Okay, let's see here. So some more informal ones. I guess I could have actually made it more formal by specifying R as the domain. But we could say,
Yeah, I guess in the formal version you can do that. Yeah, for all x and r.
yeah, for all x and R, um, if the square is greater than 4, well, for all x and R, if x squared is greater than 4, then x is greater than 2. And the inverse for all x and R, if x is not greater than 2, or if x is less than or equal to 2, then x squared is less than or equal to, or is less than or equal
Yeah,
to 4.
yeah,
So let's see. The informal one. Also, next time I might need to think twice about just how many curious mental itches are allowed to be scratched. Because I can't believe it's already been about an hour and 50 minutes, which I kind of don't mind. I guess
yeah,
if it's truly a world in which it doesn't matter what pace we get through, I guess I don't mind. I'm just, it's just
yeah,
alarming, but it
yeah,
might not matter.
yeah. It's gone by quickly. But yeah, yeah. I mean, yeah, I don't mind. We can discuss like there are a lot of interesting things to discuss. So we could discuss them yeah, yeah. Anything you're interested to discuss it. I'd be up for discussing it.
Yeah. Let's see. And another tangent. I actually changed my mind and think that you might be an INTP.
Oh yeah,
Yeah,
because I mean, I have to like this kind of thing. So
pretty much. I would say this kind of thing kind of like will like dominate your personality. Although you have like, a good handle on like politeness, right? And like courteousness and just kind of like expressing things in like the proper with the proper courteous vibe. I say like probably like the meat of your personality is kind of more in that like intellectual detachedness and like holding things in your mind and ordering the logic of them. I would say it's probably like the most salient. I think that's like the most salient uh cognitive function that you express. So yeah.
yeah, yeah, yeah. And I could definitely see that. I took the survey again. I got INFP again for the Myers Briggs. I think I got like
Yeah.
yeah. It wasn't like it was kind of close, I think, but yeah, yeah. I wonder. I have gotten both INFP and INTP, so I could definitely see INTP.
I would be really interested in seeing like at some point what your answer choices are, just so I can get an idea for why you keep testing as INFP.
Yeah,
Um, I can kind of imagine it. Cause
yeah,
like yeah, typically they'll ask a question like, which do you care about more? Like, do you care more about um, I don't know, basically like feelings or thinking, and then I guess you would have to be answering either close to neutral or to feeling most of the time.
yeah,
So, which like could be true from one perspective while also being not the perspective they expect a person to be coming at their test with. So, it'd
yeah,
just be interesting to see. Yeah, right.
yeah, yeah. I can.
Because I would definitely,
Yeah,
I
I can.
kind of, yeah, I feel like you, I'm thinking now, I'm like sold on the idea that you have an INTP composition here because you have the courteousness and you have the like salient introverted thinking tendency. Um, so from like a human perspective, from a human eye perspective, not from like a mechanical test, like a counting machine. From a human eye perspective, you definitely seem to resemble INTP. Um, but from like a test, like a mechanical counting, it would just be interesting to see, like, if you were an INTP, how you could answer the questions and test as an INFP half of the time. How would an INTP act like with this test to get INFP, or how would an INTP think about the answers? Even though an INTP and an INFP, if you see them with your human eye, they're completely different creatures.
Yeah.
Yeah.
Yeah, definitely. Yeah, yeah, I have to check out like what the questions were again and which ones could like which ones are testing F versus T.
Yeah. But yeah, I guess that shows like the flaws of the test, like its limitations are quite huge. So you can answer a
Yeah.
question that you'd be compelled to answer the F question, the F answer, and like a lot of their questions might be that way. Enough of them to where you would test as an INFP.
Yeah.
But interesting.
Yeah.
So let's see. So contrapositive, cool. Or if the square of a real number is less than or equal to 4, then the number is less than or equal to 2.
Yeah.
Converse and the inverse. In section 2.2, we showed that a conditional statement is logically equivalent to its contrapositive, and that is not logically equivalent to either its converse and its inverse. The following discussion shows that these facts generalize to the case of universal conditional statements and their contrapositives, converses, and inverses. Let P of x and Q of x be any predicates. Let D be the domain of x. And consider the statement for all x and D if P of x then Q of x. It's contrapositive for all x and D. If not Q of x, then not P of x. In particular, x and D that makes if P of x then Q of x true also makes if not Q of x then not P of x true. Any particular x and D, which is like saying like any instance, but I guess any particular x and D might be the most clearest, simplest way of saying it.
Yeah. And I guess technically the instance would be if P of X then Q of X. So like
Right.
yeah. And then the X would be just like a variable or like an item in the domain.
An item in the domain. So true. By the logical equivalence between if P then Q and if not Q then not P. It follows that the sentence if P of X then Q of X is true for all X and D if and only if the sentence if not Q of X then not P of X is true for all X and D. Thus, we write the following and say that a universal conditional statement is logically equivalent to its contrapositive. For all x and d, if P of x then Q of x is logically equivalent to for all x and d, if not Q of x then not P of x. Let's see. An example. Oh, let me read that once more. So, for all x and d, if P of x then Q of x is logically equivalent to for all x and d, if not Q of x, not P of x. Right. In example 3.2.5, we noted that the statement for all x and r, if x is greater than 2, then x squared is greater than 4, has the converse for all x and r, if x squared is greater than 4, then x is greater than 2. Observe that the statement is true whereas its converse is false. Since, for instance, negative 3 squared is 9, which is greater than 4, but negative 3 is not greater than 2. This shows that a universal statement, conditional statement, may have a different truth value from its converse. Hence, the universal conditional statement is not logically equivalent to its converse. This is written in the symbols as follows. For all x and d, if p of x then q of x is not equivalent to for all x and d, if q of x then p of x. In this exercise, at the end of the section, you are asked to show similarly that a universal conditional statement is not logically equivalent to its inverse. So for all x and d, if p of x then q of x is not equivalent to for all x and d, if not p of x then not q of x. Okay, so I guess we can stop there for now and get necessary and sufficient conditions only if on your next free day.
Yeah. Yeah, sounds good.